Netflix streams to over 230 million subscribers globally, who watch over 250 million hours of content times daily times. That's a staggering amount of data to process for recommendations. Few people know the real challenges of designing a recommendation system at this scale. We'll see why this matters when we discuss sharding. By the end of this video, you'll know exactly how to build a system that suggests the right content to the right user every time. Here's what most engineers get wrong. They underestimate the complexity of real-time feature engineering. Let's define the scope. Functionally, we need to recommend movies and TV shows. Users should see personalized recommendations on their homepage, search results, and after watching a video. Non-functional requirements include low latency. Recommendations should load in under 200 milliseconds. High availability. The system should be up 99.99% of the time, and scalability to handle millions of users. A clarifying question for the interviewer would be, are we optimizing for watch time, user satisfaction, or some other metric? We also need to handle the cold start problem for new users and items. The secret is to balance personalization with real-time performance. We also need to handle implicit feedback, watch time, clicks, and explicit feedback ratings. Let's estimate the scale. Assume 200 million daily active users, DAU. Each user makes, on average, 5 recommendation requests per day. That's 200 M times 5 equals 1 billion requests per day, or roughly 12,000 requests per second, QPS. If each recommendation requires fetching 1 kilobyte of data, we need 12 gigabytes per second of bandwidth. Storing user item interaction data. The user item interaction matrix for 200 M users and 100K items requires significant storage. If each interaction takes 4 bytes, that's 200 M times 100K times 4 bytes equals 80 terabytes. We also need to store features for users and items, which could add another 100 terabytes. Remember this, it comes back later when we discuss feature stores. That 80 terabytes figure is just the raw interaction data. Feature engineering will increase this significantly. Now that we have a solid understanding of the requirements and scale, let's look at the high-level design. We'll separate the read and write paths to optimize for the read-heavy nature of recommendations. The write path handles user interactions, implicit and explicit feedback, and feature updates. The read path serves personalized recommendations to users. Here's where most engineers make a critical mistake. They don't separate the online serving from the offline training. We need a real-time feature store to do this effectively. We use Kafka for the message queue because it provides ordering guarantees and supports replayability, unlike SQS, which lacks these features. We expose an API endpoint like get/API/v1/recommendations. User_ID equals user_ID to retrieve recommendations. The reason we use separate read/write paths is to prevent write operations from impacting read latency. We considered using a single database for both reads and writes, but the latency would be unacceptable. Let's dive deeper into the core logic. The recommendation process typically involves 2 stages: candidate generation and ranking. Candidate generation reduces the search space from millions of items to a manageable set of candidates, e.g., a few hundred. Common strategies include collaborative filtering, recommending items similar users have liked, content-based filtering, recommending items similar to what the user has watched, and popularity-based recommendations. For ranking, we can use machine learning models to predict the probability of a user watching a candidate item. We might be tempted to use a simple logistic regression model, but neural networks can capture more complex relationships between features. Your interviewer will push back. Why not just use collaborative filtering for everything? The answer is that collaborative filtering struggles with the cold start problem for new users and new items. We need a hybrid approach. We can use matrix factorization techniques like singular value decomposition, SVD, for collaborative filtering because it reduces dimensionality and captures latent relationships between users and items. However, SVD struggles with scalability for large datasets, So we might consider alternative approaches like approximate nearest neighbors, ANN, using FACE. FACE is a library for efficient similarity search and clustering of dense vectors. Stop. Think about this. The choice of algorithm depends heavily on the scale and the available data. We also need to balance exploration versus exploitation. Should we recommend familiar items or try new ones? A common mistake is not considering the exploration-exploitation trade-off. We need to consider how to balance these two competing goals. Personalization algorithms, such as contextual bandits, can dynamically adjust the exploration-exploitation balance based on user behavior and item characteristics. Now, let's design the data model. We'll use a relational database like PostgreSQL for storing user and item metadata. The user table includes fields like user_ID, created_at, last_login, and demographic information. The item table includes item_ID, title, description, genre, and average_rating. The user-item interaction matrix stores implicit feedback, watch time, clicks, and explicit feedback, ratings. We need to track data lineage by including parent_ID for augmented samples. Pause and think. What's missing from this schema? We also need audit fields like created_at and job_ID to track the origin of the data. We'll use composite keys in Cassandra to efficiently query user-item interactions. We also need to think about indexing strategies to optimize query performance. Let's talk about scaling and performance. To handle the 12,000 QPS, we'll use caching extensively. We can use a cache-aside pattern with Redis to cache popular recommendations. On a cache miss, we query the database and backfill the cache. We'll also use read replicas to offload read traffic from the primary database. To scale the user-item interaction matrix, we'll shard the data across multiple Cassandra nodes using consistent hashing. Remember those 230 million subscribers we mentioned in the hook? To handle that volume, we need to distribute the load across many machines. We can use a CDN to cache video content closer to users, reducing latency and bandwidth costs. The serving infrastructure is critical here. We need low latency access to features, so a real-time feature store is essential. We use Feast for this purpose because it allows us to serve features from both online and offline sources. An experienced interviewer will probe. What happens at 10x scale? Here's the key: horizontal scaling of Cassandra and the feature store. Consistent hashing ensures even data distribution across shards. Without consistent hashing, adding or removing nodes would require resharding the entire dataset. For reliability, we need to consider fault tolerance, monitoring, and alerting. We'll use replication for all critical components. If a database node fails, we can failover to a replica. We'll also use circuit breakers to prevent cascading failures. For monitoring, we'll track key metrics like QPS, latency, error rate, and cache hit ratio. We'll set up alerts to notify us of any issues. For example, if the cache hit ratio drops below a certain threshold, we'll investigate. We use Prometheus for monitoring because it's a pull-based system that can handle high cardinality metrics, unlike push-based systems which can be overwhelmed. Circuit breakers prevent one failing service from taking down the entire system. We also need to think about data backup and recovery strategies. In summary, we've designed a scalable and reliable recommendation system for Netflix. The key trade-offs include latency versus accuracy, exploration versus exploitation, and cost versus performance. The main bottlenecks are the real-time feature store and the ranking model. Next steps would be to implement A/B testing to evaluate different recommendation strategies and address the cold start problem by using content-based filtering and popularity-based recommendations for new users and items. We also need to consider personalization algorithms to improve recommendation relevance. Offline evaluation metrics like NDCG and MAP are also crucial. Finally, we need to build a robust model training pipeline and a model registry to manage different versions of our models.